Okay, so imagine for a second trying to organize the world using this system. Those that belong to the emperor, embalmed ones, those that are trained, suckling pigs, mermaids, fabulous ones, stray dogs. The famous writer Jorge Luis Borges actually imagined this fictional encyclopedia where animals were classified into these completely absurd categories. He even had one for those that have just broken a flower vase. It's funny, right? It's bizarre, but it perfectly highlights a very real problem we face. How do we meaningfully categorize the incredibly chaotic world around us?
Well, welcome to this explainer. Today we're doing something really cool. We are setting off on a fascinating journey inside the machine to demystify AI text classification. We're going to explore exactly how algorithms take the massive, messy, and infinitely complex amounts of text in our digital lives, from your spam folder to your social media feed, and somehow make sense of it all. Here's a quick roadmap for our explainer. First, we'll look at sorting the digital world. Second, how naive bias works. Third, decoding our feelings. Fourth, measuring model success. And finally, avoiding classification harms.
All right, let's jump right into part one, sorting the digital world.
You know when your email magically filters out spam? Or a website just kind of knows if a movie review is positive or negative? That is a classification algorithm doing the heavy lifting. But how do we actually teach a computer to do this? Unlike a human who might intuitively understand a rule like, hey, if an email says Dear Winner, it's probably spam, modern AI uses something called supervised machine learning to learn by example. We basically feed the machine a massive data set of texts that humans have already hand-labeled. Using these human-provided supervision signals, the algorithm studies the examples and learns to map completely new, unseen observations to the correct output class. It's all about learning through pattern recognition.
Moving right along to part two, how naive Bayes works.
So one of the absolute foundational tools for this is the naive Bayes algorithm. Fun fact, this was actually invented way back in 1961 for sorting library abstracts, and it is still incredibly powerful today. Let's follow the step-by-step journey of a single piece of text inside this system. First, we have the input document, say an email or a tweet. Then it gets transformed into something called a bag of words. Next, the algorithm calculates probabilities based on its past training, and finally, it spits out an output class, like spam or not spam.
Now I want to zero in on step two, because honestly, it's pretty wild. Imagine literally taking a sentence, chopping up all the words, and throwing them into a physical bag. Shake it up. The algorithm completely ignores grammar, punctuation, and word order. It doesn't care at all if the word love was the very first word or the last word. It simplifies human language by just counting how many times words like love, awful, or sweet appear in that bag. It's a very naive assumption, sure, but it makes the underlying math incredibly fast and effective.
Which brings us to part three, decoding our feelings.
But here's the thing. Human language is messy, right? Figuring out sentiment, whether someone is happy or angry, isn't always as simple as just counting words in a bag. Take the phrases, I really like this movie versus I didn't like this movie. If an algorithm is just blindly pulling words out of a bag, both of those sentences contain the strong positive word like. But a single word, didn't, completely flips the entire meaning of the sentence. This creates a massive headache for a machine trying to understand our feelings, because the word like is suddenly doing the exact opposite of its usual job. To get around this negation problem, programmers use a remarkably clever trick during text preprocessing. Whenever the system spots a negation word, like didn't or not, it literally attaches a prefix, not_, to every single word that follows it, right up until it hits a punctuation mark. So like becomes not_like. This creates an entirely new set of features for the algorithm to learn from. It now knows that not_like is a strong cue for a negative review, completely separate from the positive word like.
There's another really cool trick for sentiment analysis, which is shifting from counting how many times a word appears to just asking if it appeared at all. Because let's be real, sometimes just the fact that you use the word pathetic or catastrophe once in a review is enough to know you absolutely hated the movie. You don't need to say it 5 times. This is why a variation called binary naive Bayes clips word counts to exactly 1. It removes duplicate words before training, focusing purely on word presence.
Okay, part 4, measuring model success.
Imagine you're the CEO of the delicious pie company, and you've built this awesome classifier to detect tweets about your pies. how do we actually know if it works in the real world? Well, the crucial point is comparing our system's guesses against human-defined labels, what we call gold labels. We use a confusion matrix to see exactly where the machine gets confused. A true positive is when the system finds a pie tweet, and it really is a pie tweet. But a false positive, that's when the system excitedly flags a tweet about pie, but it turns out to be a tweet about a pie chart in a boring corporate meeting.
Now, you might be thinking, let's just measure accuracy, right? The total percentage of correct guesses. But hold on a second. Imagine we scan 1,000,000 tweets, and only 100 are actually about our pie. If I build a completely useless, lazy algorithm that simply labels every single tweet as not about pie, it would be right 999,900 times. That is a 99.99% accuracy rate. This perfectly illustrates why accuracy is a terrible metric when you're looking for rare events. Our algorithm looks perfect on paper, but it literally didn't find a single pie tweet.
So instead of accuracy, data scientists use two other metrics. First up is precision. Precision basically asks, out of all the tweets our system claimed were about delicious pie, how many actually were? It measures the quality of the system's yes answers. If it flags 10 tweets and only 2 are actually about pies, well, that's really low precision.
And we pair precision with recall. Recall asks a slightly different question. Out of all the real pie tweets out there in the vast digital world, how many did our system successfully hunt down? If there are 100 pie tweets on the internet and our system only found 10 of them, it has terrible recall. A truly good model has to balance both precision and recall.
Finally, part 5, avoiding classification harms. Moving from the math into the real world, we absolutely must examine the severe ethical fallout that happens when these classification systems get it wrong, or worse, when they learn the wrong lessons from us. Algorithms can easily absorb biases directly from their training data. This leads to what researchers call representational harms. For example, a major study examined 200 different sentiment analysis systems using identical sentences, changing only the first name in the sentence. Alarmingly, most systems assigned a much more negative sentiment to sentences containing common African American first names compared to European American first names. The AI was unjustly reflecting and perpetuating negative societal stereotypes hidden right there in its training data.
And these biases can also lead to the very real silencing of marginalized voices. Consider toxicity classifiers built to detect hate speech online. Researchers have found that some of these systems generate false positive errors, meaning they incorrectly flag completely non-toxic discussions about identities, like women, blind people, or gay people, as abuse. When the algorithm gets confused and over-censors these perfectly safe conversations, it effectively silences those communities online. So, how do we fix this? To mitigate these harms, the AI community is adopting transparency tools like model cards. You can think of a model card kind of like a nutritional label on the back of your food, but for AI. Before a developer releases a classifier, they publish a detailed card breaking down exactly what data was used to train it, its intended use, and crucially, how well it performs across different demographic groups. It essentially forces creators to look for biases before the algorithm is unleashed on the public. As we wrap up this explainer, I want to leave you with a really vital thought to ponder. As you scroll through your filtered inbox, your curated social media feeds, and your personalized recommendations, are the invisible algorithms sorting your digital life actually reflecting reality? Or are they just reinforcing invisible biases that we still need to overcome? Keep questioning the machine. Thanks for joining this explainer.